Hello everyone, today I'm going to show you something really funny, really stupid that I used to do as a kid, and it's not exactly what you might have expected, except if you managed to read the title of this video. Uh, this time I'm going to show you numerical simulation using Microsoft Excel. Why Microsoft Excel? I know there are loads of way better, way more suited softwares out there. For example, MATLAB, which we use in university, and Microsoft Excel. And you can argue about the quality of the software as such, but it's definitely not meant to be used like this. So it's not really good at numerical simulation, obviously. But when I first got into numerical simulation, I was about 12 years old. I hardly knew that it was called numerical simulations. I could not get MATLAB. Microsoft Excel was pre-installed on my computer, and it was the best number crunching kind of software that I had at the time. Uh, so I used Microsoft Excel, and I thought it might be really fun to show you because it's interesting. It's of course a little challenge to use a not quite suited software to do something that it's not meant to be used for. It's really fun. Everyone can kind of try this at home because everyone has Microsoft Excel or at least something similar pre-installed on their computer. And it has everything you need. It has a bunch of numbers, a bunch of cells that you can input numbers into, or you can input functions that depend on other cells. You have several lines, you have several columns. You actually don't need anything more than that. Everything else is just luxus for numerical simulation. Uh, Now what I did is the basic Gauss approximation, which is really simple. There are more sophisticated methods and more precise and less computing intensive methods, but this one is the most simple and most obvious, so that's what I did. Now what I did for this video is just a simple Earth, Moon, two-body system orbital simulation. Of course, you could also do that with just Kepler trajectories and everything that bundles along with that. But as soon as you have, for example, an accelerated spacecraft or re-entry with atmospheric forces or any other flight system, Kepler orbits won't quite work that well anymore. So, or if you just have a 3 or 4 or 5 body system, so that's kind of useful. And what I did back then was made I expanded on this, and I added like aerodynamic forces, and I simulated a complete winged autopilot controlled re-entry body on a direct entry trajectory from Mars, finding its way down through Earth's atmosphere to some spaceport. Now, I might continue this series and make some even more complicated things here, but for now I'm just going to show you a basic orbital simulation. So basically you divide time up into these sort of time steps. For this simulation I've taken 1 hour, that is 3600 seconds, because we use the basic SI units because that makes it easier to use all the equations without converting back and forth all the time. But I used 1 hour because I wanted several orbits of the moon, that is several months, to fit into the limit of how many lines you can plot into one graph in Excel. So I had to use rather big time steps, but they're still small enough since Moon's orbit has quite some orbital period. So 1 hour isn't actually that much, so it's still kind of precise-ish. You take these time steps, and then I set first coordinates for Earth and Moon. I set Earth as the center at the beginning, so 0, 0, 0, and then set the Moon's perigee, and I set the direction of the perigee as x coordinate, and then entered 0 into the other fields. Then velocity, I set Earth to start with 0, 0, then Moon, since its perigee, of course 90 degrees to its distance from Earth. I actually just used try and error to find the right velocity. You could of course look it up, but that's boring. Then I made a field that calculates the distance between Earth and Moon using Pythagoras. I just used fields to store the gravitational constant, the mass of Earth and the mass of Moon, and then I multiplied these masses and divided them by the distance squared, and so I got the gravitational pull between the two, which I then divided by the mass of either celestial body to gain the acceleration of both bodies. So then I multiplied it by the distance along one coordinate and divided it by the whole distance instead of doing the whole Pythagoras thing again. I just used the ratio I already had. So I got the acceleration along each coordinate, and then you can go back to the start and start the next line basically. You can say that the acceleration, that the speed along the velocity along each coordinate, along each axis, is whatever it was in the last window plus the acceleration along this axis times the length of this time step, so that you would you could put in different time steps and still the whole thing would work out pretty much automatically. And then you can say that the position in the next time step is the position in the last time step plus the velocity, and then you can repeat it all again, and then in Excel you can just mark it all and pull it down. This didn't change anything because I've already done it. Then I put it down to 1272 time steps. And I singled out two interesting numbers. That is the distance between Earth and Moon along two coordinates, or rather the difference. And I plotted them into this kind of graph that then essentially shows the orbit of the Moon around the Earth. And that's about it for now. That's basic two-body orbital simulation, not using Kepler orbits, but using Gaussian approximation in Microsoft Excel because I thought it was fun, and because back when I was 12 I didn't have any better program for this. Excel doesn't really properly scale axes, so I can pull this into any shape, but if you try to make it, wait a second, you can try to pull it so that the axes have almost the same scale, and then you get roughly the right shape. You can also scroll down here. There's also a function for maximum and minimum, so you could display the distance at perigee and apogee. Scrolling down, you can see that the coordinates change in a kind of sine wave, and that gets plotted into this ellipsis, which is the orbit of the moon around the Earth. And I actually try and error the I mean, you can just change it now. I try and error the velocity of the moon at the beginning to match the apogee to what I read on Wikipedia, because that's the most reliable source of information a 12-year-old has. And if you change it, you notice that, well, Excel automatically changes the scaling of the axis, so you don't really see how it changes, but you can see that the shape of the orbit changes if you change this velocity. I'll change it back. Now you can add other inputs into other coordinates, and of course you could now make the whole simulation more complicated, add more bodies, add something like atmospheric forces, program an autopilot, simulate an autopilot re-entering the Earth's atmosphere, which I did as a child. I might manage to find the old Excel files on some old hard drive, or I'll just build it again to show you. But for now, we're going to leave it at this slightly deformed orbit. Thanks for watching.